All right. Okay. All right, and we are back. Um, and like I was saying at the end of the last video, so now what we want to do is we want to take those frequency tables that we just, not only that we just constructed, but now we can create. We want to take those frequency tables and we want to turn them into pictures. So literally this section is about kind of technically three different pictures you can get from these frequency tables, but you'll see it's kind of one thing. Um, but let's see what pictures we can get from these frequency tables. Um, so which one did I want to use? All right, so I think we'll look at this problem actually. Um, and let me make sure we can have enough room to do everything we need out of this. So what they're doing here is, so this was some data. So kind of like, like we saw in the last video, you're given some data, you can create a frequency distribution out of it, a frequency table out of it. So here they've gone to the trouble, they've already created the frequency table for you. This one says this frequency distribution or table represents the cost in cents for the utilities of states that supply much of their own power. So this is a total of 33 states that basically supply a lot of their own power. When they say the cost in cents, the idea is basically per kilowatt hour. What's the cost? Well, yeah, for the your power. So literally, you can look on your electric bill and find that kind of information. Again, this is lacking some detail. What year was this? Was this the average over a year? Was this during a month? We don't need that detail necessarily for anything that we're going to do, but just kind of think about that kind of stuff as you're going forward. So yeah, we'd like to know a little more detail, but the point of this is they're saying in general, there are then 12 states whose cost per kilowatt hour is going to be 6 to 8 cents. There are 16 states whose cost is 9 to 11 cents. There are 3 states whose cost is 12 to 14 cents, one 15 to 17. We have 18 through 20. There's no states that cost 18, somewhere between 18 and 20 cents per kilowatt hour. None with 21 to 23 cents. But there is one state that costs 24 to 26 cents per kilowatt hour. So again, you have that data somewhere. But we went ahead and made the frequency table for you. So like I said, the point of this second section, the point of 2.2 is, well, I talked about it in the last video that already when you look at this, you kind of sort of get a picture, right? So if you're trying to analyze what is the average cost of, cents per kilowatt hour for electricity, or if you're trying to analyze kind of like what's the spread, where, what do you call it? How much does electricity cost, most often, in what do you call it? In these 33 states but really kind of in the US. Then the numbers already sort of give your head a little bit of a picture. And the thing is, we can essentially turn this table into an actual picture. And there are 2 pictures that come immediately from this table. And one of them is called a histogram, one of them is called a frequency polygon. A histogram, by the way, is just a fancy name for a bar graph. That's all we're looking at. So the first thing we're going to do is we're going to take this data and basically turn it into a bar graph. So let's do that first. Yeah, I think let's do it this way. So let's figure out the histogram. And like I said, a histogram is just a bar graph. So a bar graph what you're gonna do is you're gonna draw a bar for every category, or in this case, every class that represents the frequency, that represents how many, in this case, states had a cost per kilowatt hour in that category. So if you think about it, then one way to think about turning this into a histogram is you literally almost turn this on its side. So these categories become what you're gonna put on your call it a, give me a second, sorry. Your horizontal axis. So bar graph, usually you usually see something like this. There's a vertical axis and there's a horizontal axis. And that horizontal axis is going to be kind of your categories that you're then going to graph vertically. So that's the first thing we have to do with constructing a histogram is you have to take the categories or the classes that you have. You essentially just has to find a way to list them out along this number line. So then one of the ways we can do this, so notice the numbers that we have for class limits. We start at 6 and we're kind of jumping by 2. So 6 to 8, 9 to 11, 12 to 14, etc. So we basically need to, so one of the things that happens when you start creating pictures out of this data is you start needing to make choices. When you make a graph, backbone of a graph is you have a number line, a horizontal number line, and you have a vertical number line. So you start needing to make choices about how are you going to mark these number lines. So you capture all of on the horizontal line, all the class limits, or basically all of the numbers for the classes. And then we got to worry about the vertical axis and how we're going to catch all these numbers for the frequency, right? Actually, well, let me make that a little higher. Yes. So what I mean is our first thing you have to decide, and I guess part of what I'm trying to say here too is that, I said a little bit on the last lecture that, when you start in statistics, when we start, especially, so we organize data, now we're making visuals for our data. There's a certain part of this that is really aesthetics, right? So we were talking last time about we need our class boundaries to kind of mesh up against each other, right? It wasn't mathematically correct, but visually when you try to draw it, we like to not have spaces between these things. So there's a bit of aesthetics in how we turn this into a picture. So that means that it's a bit subjective how we number this line and how we number this line, but those are the things we have to start thinking about when we create these graphs. So for instance, on the we'll call it second, sorry. On the horizontal number line here, I need to kind of be able to capture these classes. So it looks like the lowest number I need is a 6. The highest number I need is a 26. And the numbers that I'm looking at here, it looks like I'm catching some even numbers, I'm catching some odd numbers. It basically looks like I might need to count by 2s, maybe even at least 4. So again, the first thing you're gonna end up doing here is I'm gonna put a 6 here, but then I need to decide how I'm gonna make my marks so I can count out to 26. And the aesthetics of this is, if you think about it, one way we could do this. So again, I'm going to lead with there isn't a right answer here, but we're going to look at how do we mark this out so that visually somebody who's reading this, doesn't get lost, basically. So if you think about it, one way to do this is you could mark 7, 8, 9, 10, and you could go all the way up to 26. But visually, what would be one problem? If I marked every number out to 26 horizontally, what problem do you kind of see there? There would be a crap load of lines. And so one of the things that that we know as humans, we know just as we go around and we look at things, we read books, whatever, but they've also studied in psychology is that if you have too many marks, too many lines, um, we tend to gloss over. So our brain just goes to default shutdown mode and says there's too much there to read. I can't do it, so I'm out, right? And that's an actual psychological thing. That's an actual, like, the way our brain is wired, we tend to do that. So if I'm trying to mark this bottom axis in a way that, again, what you're thinking about is you're not thinking about you, you're thinking about the reader. In a way that a reader can look at it and not gloss over, and kind of understand what they see there. You don't want to have a lot of lines. Oh. So we need marks from 6 to 26. Another way we could do this is maybe we count by, I don't know, like fives or something like that. So maybe we don't start at 6, we start at 5, and we count 5, 10, 15, 20, 25. Now, if we're gonna do that, I'm still gonna be able to make marks for my classes at all of these numbers: 6, 8, 9, 11, 12, 14, 15, 17, 18, 20. So if I mark this not by ones, but if I mark this by fives, 5, and 15, 20, 25. I could have put more space there, but what problem do you see there? That it's going to be kind of hard to mark these numbers. And if it's hard to mark these numbers, it's going to be hard for the reader to, when they look at it, they're going to be like, well, which number is that? So if I'm doing like 6 to 8, for instance, 6 is sort of maybe here and 8 is maybe here. So I'm going to draw my bar. So we're going to end up drawing bars above these. But if you look at that visually, so if this is my bar, which it's not going to be, but if this is my bar, do you know that that's 6 and 8? Not necessarily. So if we draw too many, what do you call it, too many marks, too much detail, our mind just glosses over and says, I'm Audi 5000, right? But if we don't have a lot of detail, if we draw very few lines, the problem is the lack of detail makes it so I can't read the numbers and the values that I'm dealing with well. So when you're drawing a graph for a reader, you can't have too few lines, too few details, because then they can't really read the numbers that are going on there. But you also can't have too much. Having a lot of lines gives you the detail, but the reader is just going to be out. So you need kind of somewhere in between. So I call this kind of the Goldilocks principle. So your porridge can't be too cold or too hot. It needs to be right in the middle, just right. So we need a number when you're figuring out what what number to start your in this case our horizontal number line at, and what to count by. You want something that gives you kind of instinctually not too few lines and not too many lines, something sort of in between. So I can give you guys kind of a rule of thumb. When I say it's a rule of thumb, I'm saying that, so again, because this is about visual aesthetics, psychology, the way that we read stuff, there's not necessarily a right answer here. And there's not even necessarily a right answer for every situation, definitely. But there's not necessarily a right answer, but there's sort of, like I said, there's sort of a middle area. So there's not Goldilocks, not too few, not too many. There's sort of a middle area that works well for most, definitely all the problems we're going to look at, but most diagrams that you're ever going to have to create. So in general, the way you want to think about this is if I've got a count, in this case from maybe 5 up to 30, maybe. The point where you start hitting too many is roughly at about 10 marks or 10 lines. And the point where you start hitting too few is probably 5, even 6. So you want somewhere between roughly 7 and 10 lines or marks so that the reader has enough detail that they can really see the numbers, but also there's enough space and not too much detail so that their mind just zips out and can't really read what's going on. So somewhere between 7 and 10 lines, I would say, is a good rule of thumb. So I need to mark, we need marks that cover everything from about 6 up to 26. I'm gonna go a little below, so I'm gonna go down to 5 and up to maybe 30. So again, if I count by fives, there's 5 up to 30. If I count by fives, it's still gonna be too few. I need 7 to 10 or so. Let's see. So again, there's not one right answer here, but I need to get about 7 to 10 lines there. I think the way I would do this, let me think about this for a second. Actually, is that the way we want to do it? That work? Yeah, that does work. So what I'm going to end up doing here is I'm going to count by threes, and I'll show you kind of why I decided to count by threes. But I'm going to count by threes. Because if I start at 5 and I count by threes, 3 gets me up to 8, and then the next 3 gets me up to 11, and then the next 3 gets me up to 14. And suspiciously, what do you notice about these numbers that I'm writing? That they all actually match the ends of our classes. And then there's 17, then there's 20, then there's 23, and then there's 26. And now essentially each of these spaces matches one of my classes. So my first class is going to be from 6 to 8, so technically I'll write my bar a little short. Then my second class is going to be from 9 to 11, so that'll be my little bar there. And then from 12 to 14, etc. So each of my bars fits very nicely into the numbers that I just put on that number line, but I was counting evenly. I didn't just put the numbers there. I actually was counting by threes, and it happens to land on each of these numbers. Now also notice that class width here is 3. 9 minus 6 is 3, 12 minus 9 is 3, 15 minus 12 is 3. So I would say, honestly, for the horizontal axis, if you can count by the class width, then it's going to always turn out like this. Your bars are going to just magically nicely fit into well, the little slots that you're creating there. So this captures all of my little classes. Now on the vertical axis, I got to capture all my frequencies. So take a look at the numbers there, all your different frequencies. And once you got kind of those, stapled into your head, again, what you want to do with the vertical axis is you want to count. So you want to figure out kind of a low and a high number, and you want to have enough lines there. So again, 7 to 10 lines. You want to count in such a way that you're going to get about 7 to 10 lines. And also you want to think about just the numbers themselves that you're trying to cover. So you want to make sure it's going to be clear to the reader, for instance, that 3, on our bar that's 3 high, that's a 3, that the reader is going to see it. And even if there's not an exact number there, they're going to know it's a 3. So for instance, here we got to go from 0 to 16. And I need my bars are going to end at 12, at 16, at 3, at 1. So I have a couple that are going to be 12 and 16. If you think about it, you could count by 4s and you would hit those. But then the 3, you'll probably tell where the 3 is. It'll be kind of just below the 4. And the 1 is going to be pretty close to 0. So one way we could do this is we could count. So for our frequency, we could count by 4s. But if you do that, notice that you're going to have a bunch of space there. And so again, this is going to be this is maybe too few lines, and it might be hard for the reader to catch every number that you're trying to communicate there. But instead, if I count by twos, this is gonna be a lot better because then, for instance, my 3 is halfway between 2 and 4. I can show that very, very well. Very, again, the reader, when they see something that looks like it's halfway between 2 and 4, your mind automatically says that's a 3. I don't even have to label it. It doesn't even have to actually be exact. As long as it looks like it's halfway between 2 and 4, your mind is gonna tell you it's a 3. And the 1 is halfway between 0 and 2, so if I mark something halfway between 0 and 2, my mind is gonna tell me that's a 1 automatically. So in this case, for the numbers we have here, it's actually a really good play to just count by twos on the on the frequency axis, or on the vertical axis, so for our frequency. So creating a histogram, literally every time, your first job is actually to figure out how you're counting or how you're setting up your horizontal axis, and then how are you counting on your vertical axis. We're going to show you frequency. And then what I'm going to do is I'm going to draw a bar for each category, for each class, that matches the frequency that we see there. So for instance, from 6 to 8, so there were 12 states where it was 6 to 8 cents per kilowatt hour. So I'm going to go to the 6 to 8 category, here to here. I'm going to draw a bar up to 12. And there we go. Let me see something in the book. So this is another thing that, depending on the book, some books don't care if they want, like, if the bars don't meet each other, and some books kind of emphasize that they should. It's not technically correct, but it's aesthetically pleasing. So let me just see what this book thinks. As if you're using boundaries. Well, so well, I guess let's just kind of be naive and draw this kind of as it would come out naturally. Then I'll show you kind of why some books technically draw this slightly differently. I mean, it's gonna be like I was talking about in the last lecture, it's gonna be the same numbers, concepts, and ideas. It's actually the same thing. But we'll just kind of talk about the aesthetics of it and why they draw it differently sometimes. So from 6 to 8, it's 12, and then from 9 to 11, it's 16. So let's look at this the horizontal axis. 9 obviously is not here, right? So 9 would start roughly, where would 9 start? Like a little to the right of 8, right? So maybe 9 starts there. So I would draw my second bar like this, up to 16. And then you would keep going. From 12 to 14, you would draw 3, 1, etc. This will be easy enough. You guys will do this easily. The one thing, again, I want you to realize that fancy word histogram, it's just a bar graph. You've been doing bar graphs since likely 6th grade. So this is really, really easy. This is not meant to be hard. And if you're finding it easy, you're not doing anything wrong. You should rejoice, because it really is this easy. It's just a bar graph. So let me have you guys finish out this histogram. And then, like I said, we'll talk about some of the aesthetics of it. So go ahead and pause on your side. I'll pause on my side. All right, do it. Let's see what you guys have. So like I said, really easy, really simple. From 12 to 14, that's 3. So halfway between 2 and 4. Something like that. Make that a little lower. Something like that. Now from 15 to 17, it's a 1. Something like that. 18 to 20, it's a 0. So you would just have nothing there. Often, I mean, you literally just draw nothing there. And same for 21 to 23. And then 24 to 26 would also be a 1. So that would be the graph. What do you call it? Yeah. That would be the histogram of this data, this frequency table. So just a good old fashioned bar chart. Let me actually check on the Polygon. They do it. So that's the histogram of the data. So I was saying that we're going to talk about some aesthetics. So you'll notice a lot of the pictures they're going to show in the exercises. What this book tends to like to do is, so it doesn't like aesthetically, it doesn't like the fact that there's spaces between these bars. Now, there's nothing mathematically wrong with that. It's actually mathematically accurate, and there's not even anything artistically wrong with that. But I kind of understand the ideas aesthetically. It's like seeing these spaces like gives you sort of a jarring look. Whereas instead of seeing those spaces, what we could do is basically the way to think about this is you can use the class boundaries. So you can, we were talking about the class boundaries meet each other. So we can use the class boundaries to essentially close this up. And so like literally, I'm gonna extend that first one the right 0.5, and I'm gonna extend this one to the right 0.5 as well. And voila, there's no space anymore. And depending on your aesthetics and how you like to see things, this maybe looks a little more beautiful to you. So you'll often see bar graphs basically are usually, not just usually, they are written either with spaces between the bars or with no spaces between the bars. So note for these problems, if there's no spaces between the bars, what they're doing and what they're asking you to do is to essentially use the class boundaries, just that little extra 0.5 on both sides. So for instance, here would move this one a little bit that way. So like this and like this, and then we would move this here. And we would, oh, oh, technically move this a little here. Then for this last one, yeah, sure. Move it a little here and move it a little here. So using the class boundaries instead of the class limits, using that extra 0.5, it would look something roughly like this. Now I keep saying that it's aesthetics. Notice that it didn't actually change, in some sense, it didn't actually, not just some sense, it really didn't actually change the look of the graph. And it didn't change the look of kind of so one of the reasons I don't like that they were using the word distribution in the last section, so I kept on calling it a frequency table, is distribution is usually reserved, classically, it's reserved for, like it describes a picture. So distribution essentially is the picture of all of your data values, and visually what picture does, like how are those values distributed? But how are they distributed in terms of a picture? So I would say honestly, this is actually a distribution. So this is the distribution of the data values. You get kind of this picture, and notice that that picture kind of looks the same whether your bars meet each other or whether there's space between them. So this is a histogram. Um, oh yeah. All right, so like I said, so again, this is your table, this is your raw data turned into organized at least, right? So this isn't the raw data, but it's the raw data organized. And this is now your organized data as a picture. And so you see kind of this visual now for how the data is spread between all these little these categories, these classes. So if I asked you, for instance, you know, what's the most common or what price in kilowatt hours happens most often, what would you say? Good. So you literally can just look at the tallest bar and you got it. You'd have to know again that this is really trying to say 9 to 11. One of the reasons that I don't like them having the bars meet, aesthetically, it looks very pleasing. Not only that, I mean, it shows this, you get this nice shape. But notice if I'm gonna answer that question, which class or which cost happens the most? From the table, the answer is 9 to 11. But if these bars meet, it's kind of hard to see that 9 to 11 is the answer there. So that's the only thing I don't like about that personally. Um, and again, like I said, this is the part of statistics that's subjective. Um, I understand why they like to have this, but I think it doesn't read well because you can't see the numbers as well. So anyways, but your answer would be 9 to 11. So majority or most states, there are more states than others that charge somewhere between 9 and 11 cents per kilowatt hour. Something else you can sort of start to ask about data is, you know, so like I said, this is the distribution of the data, is so not just what happens the most, but where's the data spread? So what range of prices are you going to get most often? So not what single price or single category, but what range of categories do you get more often than not? And so that maybe that's my question, to you guys. So what now, not single class, but what range of what do you call it, costs happen more often than not? So notice basically from here to here, you pretty much have almost all of your states. Again, we can see it here. 28 out of the 33 states cost somewhere between 6 and 11 cents per kilowatt hour. So that would kind of be the answer to that. That the range or the spread from 6 to 11 cents is about where, you know, is where most states are. So thinking about where not just a single category, but where in this diagram the range where most of your data lies is something called the spread of the data. And we're going to look at several things as we go through in this course, ways that we can calculate that spread. So right now we can see it with a picture. Notice so we can see it with a picture and that's good. You can physically see where most of that data is. But that is, you know, that is tied to the picture and the picture is a little bit subjective, right? So as we go through this course, we want to look at, is there ways that we can calculate that spread? We can calculate what that spread actually is. And also I was asking you which price or which category happens the most, which price point happens the most. That's well, in statistics, what we call a measure of central tendency, but that's just a fancy word for an average. So you guys have been seeing averages and calculating averages again since probably sixth grade. So we want to know the average cost or or the cost that happens the most, right? So that too, we can see it. So right now we can see it from the picture, and these pictures are easy enough that we can get an accurate answer. But if the pictures are more complicated, then the picture is not going to tell us the answer. We need to have a way to calculate the answer. What is the average, or what do we expect the price to be, right? So averages, measures of central tendency, and spread are two things we're going to study a lot in this course. And so right now we're going to answer most things like that using the picture, but as we go, we'll get some more exact ways to calculate averages and spread. So good. All right, so this is a histogram of this data. there we go. It's like, they also, another thing they'll ask is you to make out of this data is what's called a frequency polygon. And if you compare the word histogram and frequency polygon, it sounds like frequency polygon is just some completely different, almost literally like this is Mars, and suddenly they're asking you to do something completely different, like go to Venus, right? So completely different planet. But the interesting thing is actually frequency polygon comes from the histogram. It comes, yeah, it just comes from the histogram. So the frequency polygon uses the same exact setup as the histogram, so you don't have to do anything different with your axes. The idea of the frequency polygon is we're basically going to do this graph over again, but instead of doing bars, we're gonna graph points at the midpoints of each of these classes. And then we're basically gonna connect the dots. So a frequency polygon ultimately, honestly, is it's a line graph. And we'll talk about why they call it a polygon. I think it's just another one of these, it's an weirdly overworked and overcomplicated name. But it's essentially a line graph. So going back to what you guys have seen before, again, a histogram is a bar graph. A frequency polygon is a line graph, basically. So you've got this table, you made a histogram. Now they want you to make a polygon, a frequency polygon. So like I said, you don't change anything about these axes. All I'm gonna do is I'm gonna take these bars out. Take all these bars out. But for each bar, instead of having a bar there, what I'm gonna do is I'm gonna find the midpoint of each of these classes, and I'm gonna mark the 12 there. So literally, instead of just drawing a rectangle, all I'm gonna do is mark a point at 12 using the midpoint of each of these classes. So for instance, 6 to 8. What is the midpoint of that? What's halfway between 6 and 8? So we were talking last time, maybe you need to calculate that, and if you need to, run that through. But even if you needed to calculate it, you can probably see it pretty easily that 7 is halfway between 6 and 8. So at 7, I am going to mark 12. And then halfway between 9 and 11, I'm going to mark 16. What's halfway between 9 and 11? That's a 10. So then at 10, I'm going to mark 16. What's halfway between 12 and 14? What's my midpoint there? It's 13. So at 13, I'm going to mark 3. And then what's my midpoint here? 16. So at 16, I'm going to mark 1. Like that. And then what's my midpoint here? That's 19. At 19, I'm going to mark a 0. So I'm going to put that down there. At 22, I'm going to mark a 0. Then at 25, I'm going to mark a 1 again. And are they using boundaries or limits? This earlier in this section. Probably doesn't. Okay. So I've marked every category, every class, I've marked the amounts. I'd say the one thing you have to kind of keep in mind here, the one thing they do here is basically they want you to be able to, they want a point at either end of this, sort of the left side and the right side that just kind of caps it off. So again, this is an aesthetic thing. So for instance, basically at 5.5 or wherever, we would have a point down here just to kind of cap off this end of our data. And then at 26.5, we would have a point down here. But once you have that, all you do is you connect the dots with straight lines. So you literally just play connect the dots. This is the frequency polygon of that data, of that frequency table. And they call it a polygon because if you think back to your geometry class, a polygon is any closed straight-sided figure, and that's what we have here. So by putting these ends there, what we have now is a little closed, weird figure that is not any type of normal, that's not a pentagon, I mean, technically it's probably one of those, but it's not a regular pentagon, hexagon. It's not the nice shapes that we're used to, but it is a polygon. All a polygon is a bunch of straight sides that eventually come back onto each other, right? So this is a polygon about frequency. It is a frequency polygon. But like I said, honestly, besides these ends for line graphs, you never usually put these endpoints on. But besides those ends, this is a line graph. That's all it is, really. And so you're going to see actually quite literally almost every problem in this section is here's a frequency table, or maybe you have to come up with the frequency table yourself. But once you have it, they're going to want you to make a histogram, and maybe they're going to want you to make a frequency polygon also. And you just replace the bars with points and draw your lines, and you're good. The last visual, the last graph that they want you to be able to create out of this section is what's called, this is Ogive. I just found out that the way you pronounce that is Ogive, which actually kind of makes sense. This is another, like, you're gonna hear me say a lot. This is that, when we're talking about vocabulary, this is a fancy word for this, right? This is just a weird word for this, and for this simple idea. I have no idea where they got this word for. This is not just like a fancy word. This is like they pulled a word from Saturn or something like that, like completely different language, galactic empire. Like I have no idea where this word comes from at all. The way you want to think about this though, so an ogive, and actually let me see, is it a histogram or is it it's a histogram? I know. It's a line graph. Pretty much the way you want to think about this is an ogive is a frequency, it's going to be a line graph, basically a frequency polygon. It's going to be a frequency polygon, but for the cumulative frequency. So remember on that last video, we did all those problems with the frequency table, and then right at the end, we talked about making a cumulative frequency table. So it's literally just an extra, essentially, it's just an extra column here where you add up all of your numbers as you go. So you're basically, for every category, you're not saying how many data points are in that category, but how many data points do you have all the way up to that category for everything before it. So the ogive is literally just the line graph for the frequency polygon for the cumulative frequency. That's all it is. And by the way, you could also make a histogram for your cumulative frequency. And I think there's a question or two on the homework that does that. So again, once you have your cumulative frequency, they can ask you to make a histogram for it, a bar graph. But if they ask you to make an ogive, that's specifically a line graph for your cumulative frequency. So we want to make the ogive of this frequency table. So that means we're going to have to, first of all, fill in a cumulative frequency. Man, that combination of words is so long. We're gonna have to make a cumulative frequency column. And we're gonna use that information and make one of these, but um, sorry, but with the cumulative frequencies there. When we did cumulative frequencies on the last video, your rows would say like less than 8, less than 11, etc. Just pretend your rows say that here. That whole way that they wrote it, and that actually that, you know, so that's the way the book wrote it, and that I showed you guys on the last video, the less than. Honestly, this is the first book I've ever seen that writes it that way. Usually for cumulative frequency tables, it's implied that your frequency here is everything less than the category you're looking at. So usually they don't rewrite the category. They still give you the same class, but it's intoned. You know what the word cumulative means. So it's intoned that the frequency there is not the amount in that category, but in that category and everything before it. So I'm saying all that to say, like, the cumulative frequency stuff we're going to do from here on out, I'm not going to write the less than because it's cool. It's very descriptive, but it's actually not the way you're going to see it written most of the time. That's just something, a cool thing that this book does, but it's actually not very common. So anyways, so for these cumulative frequency, you can just figure out each of these classes. It's just, again, everything up to that class. So what I'd like you guys to do is then go ahead and figure out the cumulative frequency here, and then see if you can draw the line graph or the frequency polygon for that. And we'll see what you get. So, but if you can, then we'll see that's your ogive. So go ahead and pause on your side. I'll pause on my side, figure out the cumulative frequencies, and then figure out the line graph for that. The ogive. All right. Let's see what we got here. So for your cumulative frequencies, so up through 8 cents kilowatt hour, that's 12 of the states. But then up through 11 cents, that's going to be 12 plus 16 is 28. So you get a 28 there. And then from up to 14, that's going to be 31. Up to 17, that's going to be 32. So again, you're just adding everything, you're including that and adding everything for it. So then the fun thing is when you get to 18 to 20, I'm adding nothing to it, so it's still 32. So I'm going to sort of plateau out at 32 for 18 to 20 and 21 to 23. And then I'm going to bump finally up to the full total, 24 to 26. 33 from 24 to 26. So that would be my cumulative frequencies. So now what I need to do, like I said, is we need to come up with the OG for this, which is going to be more of a proper line graph. So it's going to be a frequency polygon, but we'll talk about, you're not going to do this end part. But notice before we even get there though, so like, let's not worry about that yet. Notice these frequency numbers. These are a lot different than the frequency numbers I saw here, because again, this is cumulative frequency. So when I go to graph this, when I go to make my little frequency polygon, you can kind of think about your horizontal axis is going to be the same, but my vertical axis is going to have to be a lot different because this one only goes to 16, counts by twos. Looking at these numbers, what do we need to get up to here? We need to get up to 33. And we've got quite a few other numbers to hit. But we got to hit a 12, we got to hit a 28. We can't guarantee that all these are going to be right on a line, but they need to be close enough that, or kind of like this was set up, the interval set up so that your mind knows exactly what number you're looking at, right? So let's look at these numbers for a second. So we're gonna, to make this frequency polygon, we're gonna import, copy paste the horizontal axis, but the vertical axis has to change. So by the way, the vertical axis is always going to have to start at 0. So we're gonna have to start at 0, but now we gotta get up to 33. So think about kind of then, how do we wanna mark out the vertical axis? What do we wanna count by? So that we catch kind of at least most of these numbers. What you guys think? All right, and again, there's not one right answer. I think probably the best play is to count by fours, because 3 fours is a 12, 7 fours is a 28, the 32s, or even that's 8 fours. So basically, if we count from 0 up to 32 by fours, that'll be 8 lines, and that'll actually catch almost everything we need. And then we'll just need one line after that. So we're basically actually going to count to 36. But that'll catch everything, and almost all of our data is going to be right on a line. So it'll be easy. Again, when the person reads it, they'll be able to know what number that is. Okay, so that's the way we want to go about this. So the ogive here. I keep on wanting to spell with the J because of the way they pronounce it. So the ogive here. Then my bottom is going to be the same here. I guess I'm going to start kind of, I guess we'll start at 5 and yes, count by 3s. So that's an 8. It's an 11. That's a 14. That's a 17. That's a 20. That's a 23. That's a 26. And then vertical axis, I decided, but we decided we would start at 0 and count by fours and get up to basically 36. 4. That could be too much. 8, 12, 16, 20, 24, 28, 32, 36. We got to go up a little farther. 4, 8, 12, 16, 20, 24, 28, 32, and 36. But then, like I said, this is a line graph or a frequency polygon. So I'm not going to do bar graph. I'm not going to do bars. I'm going to use dots. I'm going to start my, so for each, yeah, basically for each of these. So just like we did for the frequency polygon. So again, same thing. We're going to put these on the midpoints. So at 7, I'm going to put 12. And then I'm going to go back to basically 5.5, or basically the corner here. I'm going to put 0. So it starts at 0, obviously, and it goes up to 12 at 7. And then at 10, it's going to go up to 28. So that'll be up here. And then at, 10, at 13, it's going to go to 31. That's not going to be much higher. That's just going to be a little below 32. So at 13, it is a little below 32. So something roughly like that. Then at 16, it's actually at 32. Then at 19, it remains at 32. And at 22, it also remains at 32. And it creeps at 25, it creeps up 33. Just a little one. Something like that. And so this is the ogive. Now, the one difference between this and a frequency polygon, so like I said, it's your method is frequency polygon, but you're not gonna cap it off on the right side. You're gonna start at 0. So you're gonna start on, you are gonna do it on the left side. What we're doing on the left side is since this is a cumulative frequency diagram, again, the idea is how many states are we accumulating? How many data points we're accumulating? So we have to start at 0. We have to have a sort of a place in this graph where there is no data points that have been accumulated yet, so that we can then start adding, we can start rolling those data points in. We can start accumulating data points. So we need a 0 point here, but On the right side, we want to know when visually, we want to see when we get to all of them, right? When we get to all the data points. So we don't want to bring this back down because then it's going to look like we suddenly drop off and go to 0 data points. So you are gonna connect it dot to dots. This, like this, straight across, up. That is your ogive of the cumulative frequency data. And honestly, that is this section. They're just asking you to turn a frequency diagram into a histogram, frequency polygon, and the cumulative frequency into ogive. The one other thing they introduced in this section that we didn't see in the previous section, is they introduced what's called a relative frequency table. And then, but then they ask you to do the same thing, histogram, polygon, ogive. So let me just kind of introduce the idea of a relative frequency table to you guys. And kind of see how many of those 3 diagrams we want to do. But before we get there, what I'm saying is actually, that's actually it. That's this section. All right, so let's look at relative frequency. Oh, actually, I'm sorry. There is one other thing. Sorry. There is one other, I won't say thing, but there's one other bit of information that they look at in this section. So actually, let's look at that first, and then we'll do relative frequency. So this other bit of information they look at. So just in general, like kind of take a look at what we have here. Once you have, sorry, I guess let's move this back down. So once you have these diagrams or these pictures, these graphs of our data. So now we have graphs of the data, not just tables of the data. Like I was saying earlier, these graphs, they have a shape to them, right? Like you can see the distribution, you can see how the data is spread out. So maybe you see it as a polygon, maybe you see it here as a cumulative little line creeping up. Maybe you see it as a bunch of bars back to back, but we kind of have a picture of the distribution of the data. Once we have that, we can start talking about visually how the data is spread out or distributed. And there's some pretty common, so like for instance, this picture that you're seeing here, surprisingly is actually decently common for a lot of data. So like this is the particular picture for this particular data. But a lot of data, a lot of experiments, when you run them, end up looking like this if you do a frequency polygon. So obviously the numbers aren't going to be the same, but the overall shape is the same. So the kicker is, and the key here, the kicker is that this overall shape, the overall shapes that we see in our histograms or our frequency polygons are often very similar to each other. So there are certain shapes that we come up with often. So I want to show you kind of what those shapes are. See. And we could still. All right, so these are shapes that come up often when you go ahead and graph data. So you run an experiment, again, whether that's for psychology, sociology, business, economics, whatever. You go ahead and get a frequency table going on the data, and then you get, let's say, histograms. So let's focus on histograms. A lot of times, and this is weird that it ends up this way. This is actually going to become a theme in this class. Hopefully it'll become like really like Twilight Zone weird, like out of this world weird to you. A lot of times you end up with what's called a bell-shaped curve, bell-shaped distribution. And it is weird. We don't necessarily, I think numerically, so from a calculation standpoint, it kind of have an idea of why when you have a bunch of data, it often ends up like this, where essentially you have most of your data is grouped towards the middle of the range of values that you're looking at, and you kind of tails off on the left and tails off on the right. So from a calculation standpoint, maybe there's some reasons that make sense. But from a functional standpoint, like why would a lot of experiments on very different scenarios? Again, so when I say a lot of experiments, I'm saying a lot of experiments in psychology, sociology, biology, physics, chemistry, economics, things completely unrelated to each other, right? A lot of them end up looking like this. And so I think there's a giant philosophical question there, like why does the universe present data like this in all these different situations that have nothing to do with each other? What is that about? I'm not even saying I have an answer. I'm just saying it's a definite weird, it's weird. But it's a definite pattern. And so we'll talk about it later in this class. They have a way to maybe not explain it, but at least describe it. They call it the central limit theorem. Um, but but besides that verbiage, those words, you don't want to let the words kind of like basically give you a definition on something we don't really have a definition on. We don't know why. We don't know why the universe and experiments tend to work this way. But a lot of them, not all of them, but honestly, a lot of them, definitely the overwhelming majority end up looking like this. And we don't know why. It's weird. But some other distributions, some other shapes that come up often as or basically for the rest of the experiments that don't end up looking like this, the ones that come up most often is uniform distribution. So the idea here is that everything is about even. So basically we're saying all of these results come up roughly the same amount, roughly the same probability, same amount of times. This happens a lot when we have processes that are very exact. So like in manufacturing, right? So when you make a Toyota or a Honda, right? You want those parts to be almost the exact same size every time so that they can fit the exact same size every time. So, so you want things to repeatedly be the same, right? So things like that, you tend to get uniform distributions. I was telling you guys about how in statistics in particular compared to algebra, they keep introducing new terms or things keep changing slightly over time. This J-shaped and reverse J-shaped, this is the first textbook, statistics textbook I've ever seen name these. Or like this is literally the first time that I've seen it. And again, I'm a mathematician. I have 5 published papers and a lot of citations to a couple of my papers. First time I've seen these. Now, is it the first time I've seen these shapes? No. Is it the first time that I've noticed that a lot of the experiments that don't end up bell-shaped end up looking like this? No. I've noticed that privately to myself. I've seen enough research to see this shape a lot and notice that it kind of comes up very often. But literally, whenever this book was published was probably a couple of years ago. This then is the first time that anybody is given a name to that shape, that distribution of data that we all as researchers have seen often, right? So again, if it's not bell-shaped, a lot of times it's uniform. A lot of times they're calling this J-shaped and reverse J-shaped because it kind of looks like a J, basically. But it basically is a distribution that kind of goes from low on one end to high on the other. And it's a pretty constant little curve up. And reverse J-shaped then is going to be high on the left end and curves down to low on the right end, right? This comes up decently often when it's not bell-shaped. Another two that come up decently often is right skewed and left skewed. So notice right skewed, the way you want to think about this. So the naming on this is weird. I've always disagreed with their naming on this, but if you compare the skewed graph, so forget right and left right now. If you compare the skewed graph to the bell-shaped graph, what do you see or what do you notice? Notice that they're kind of the same. Except for, so basically a skewed graph is a bell-shaped graph that's been pushed one way or the other. Like where literally the the mound in the middle has been pushed one way or another. So if I take this bell-shaped graph and I kind of push it left, I get the right skewed graph. Now, I've always thought that it should be named left skewed graph because you're pushing the mound, the top of the hill, to the left. The reason they call this right skewed, the skew is in reference actually to, well, anyways, the reason they call this right skewed is because the tail of it, the low end of it, is on the right. So they name it by where the low end of it is, which is just really weird to me. Should name things by their major attributes, not their minor attributes. But anyways, so this is a right skewed graph. It is a bell-shaped graph that's been pushed. The major part's been pushed to the left, so the minor part is on the right side, right skewed. And a left skewed graph is a bell-shaped graph that's been the mound, the major part has been pushed to the right. And so the low part is on the left. Notice for both of these though, now, like the right skewed graph, mound has been pushed to the left, but notice you still kind of basically have a little bit of a downslope. You have a downhill on the left as well. So in some ways, what I'll have you do really quick is compare the right skewed graph to the reverse J-shaped graph. What's the difference? What's similar and what's different about those two? Good. So notice they kind of are similar, like the right skewed graph and the reverse J-shaped graph, they're low on the right and they go up. The difference is the reverse J-shaped graph just its top, or its what do you call it? Its maximum is all the way on the left. Whereas with the right skewed graph, you get a maximum and then it goes back down a little. So you still get a hill there, basically. Here you don't get a hill, it's just a slope up. So that's really the difference. A right skewed graph, you can also think of it as a reverse J-shaped graph with just a little hill on the left. It doesn't top out all the way on the left. And a left skewed graph is like a J-shaped graph. It just doesn't top out all the way on the right. There's a little bit of a hill there. Then we have kind of these. So again, these are another two distributions that come up a lot. Again, when it's not bell-shaped. So this one's called a bimodal graph. You guys have already seen probably in a previous math class, mode is one of our ways of doing what happens the most, or average. So if you look at a bimodal graph, it's literally two bell-shaped graphs kind of stapled back to back. So it has two modes, or it has two things that happen the most. So if I asked you what's the average of this graph, or what would you expect to happen more often or most, you couldn't say one thing. You would have to say, well, this number, this thing, and that thing, this class and that class. And you could have trimodal graphs, by the way, quad, but more often than not, if you have more than one average or mode, it happens like this. It's usually two of them. So this is a bimodal graph. It is two hills, two bell shapes. And then finally, we have the U-shaped graph so notice the U-shaped graph in some ways is also a bimodal graph. It has two modes, two things that happen the most. But instead of those most being sort of in the middle of a hill, these most are on the end of the graph, so on the left end and the right end of the graph. So literally the idea here is you can kind of trace it out. This is like a U. You could also think of it, it's basically like a J-shaped and a reverse J-shaped graph stapled together. That kind of like this one stapled there. But more importantly, so basically these are two graphs where you have two modes or two averages. And when you have two averages, you almost always see it this way. You see it as two hills, or you see it as high on the left, down in the middle, all the way to high on the right. So these are, when I say common, I'm saying these are very common distributions, but I'm also saying, not that you don't see other weird looking distributions that don't exactly match these, but this actually kind of catches. So that, again, weird thing about the universe, you get an experiment going on something random. Doesn't even have to be something you like, whatever, just some weird, just some something that's happening in the universe, or with people, or in the brain, or with economics, or whatever. Almost every time you get one of these graphs. Like, I can't think of a ton of examples that I've seen in my own personal life and research that doesn't fit these. So every once in a while, you'll see something weird and different. Otherwise, almost everything in the universe, every collection of data in the universe. So what I'm saying is basically almost every collection of data in the universe, and I know this is hard to believe, but I won't put a percentage to it, but it's really, really high, probably 98%. Every collection of data in the universe, almost every collection of data in the universe looks like one of these. And that's a weird thing. Why would it be so few? Why would everything sort of tend to look like each other when you just throw a bunch, when you just have a bunch of data from an experiment? And I don't have an answer for that. I'm just saying that's a good, interesting thing to think about. You can think about that for a long time. All right, so those are the kind of distributions of basically the histograms that we see almost always. You look at data. Right. So let's finish with maybe one problem where we have to do relative frequency. Talk about that. Then so really quick, another thing about showing you those, showing you those distributions, and then you have names for them. So you're going to see problems where once you've graphed your frequency polygon or your histogram, they're going to ask you, what is the distribution like? Like, what shape is that? So that's also why I gave you guys all that, not just for the philosophical question that will make you think probably for the rest of your life, but also just practically so that you can give names to the histograms that you're coming up with as you're doing these homework problems. So, okay. Concepts we don't need. Didn't really do it with any of these. So give me a second. I'm gonna pause. Give me a second to figure out which of these I want to do a relative frequency diagram with. All right, so I think let's actually look at the info number 12 here. Let me erase all this, but let's look at the info on number 12. Well, we're just gonna need to recreate these things anyways, but. All right. So, and I'm gonna turn this problem just is regular frequency distribution, but I'm gonna turn this into a relative frequency problem. So there are some problems where they're gonna ask you not to graph the frequency, but the relative frequency. So let's kind of talk about what that means. So relative frequency. So the word relative, what does that mean to you? Or what does that mean? Give me some other word or meaning that kind of comes to mind when you hear the word relative. Good. So maybe it's something kind of related to you, right? Like it's something sort of not you or not the thing, but like it. Something you're comparing it to, right? So, a relative in a family, or, the position of the moon relative to the sun, right? They're both similar objects, not really, but they're circles. But so they're both similar objects that we're tracking their apparent position, and so we're comparing, right? So the key word there is comparison. So relative, we look at things relative to each other, where in some sense we're comparing them to each other. So in math, relative always means percent. As percent is our way of comparing an amount you're looking at to a total. Well, that's literally what a percent is. The amount that you're looking at, or the number that you're looking at compared to, divided by a total and turned into a percent, but compared to a total, right? So for instance, this problem is talking about, this is the frequency distribution for the waiting times in minutes for 50 patients at a walk-in medical facility. So this is like, like emergency ER, the emergency, urgent care or something like that. And these are 50 patients that walked in, and then they recorded on the way out how much time they waited, or maybe the people, kind of maybe not the nurses because they got more important things to do, but some of the people on duty kind of recorded, when the people came in and then when they actually got back to get seen, and they just kind of did subtraction and figured out how much time the people waited, right? And so this is the frequency table that comes from that. So out of 50 patients, 7 waited somewhere between 11 and 15 minutes, 9 waited 16 to 20, 15 waited 21 to 25, 9 waited 26 to 30, etc. So this is frequency. You just count how many times it happens. Relative frequency is, we're going to figure out for each of these frequencies, we're going to figure out what portion, what percentage of that, of the total is that. So there was 7 patients who waited 11 to 15 minutes out of 50 total. So 7 out of 50. Well, again, I'll show you how to calculate it once. So 7 divided by 50. What decimal and then what percent is that? So go ahead and kind of do that really quick. 7 divided by 50, what percent is that? That is 0.14, which is 14%. So the frequency, 7 out of 50 people waited 11 to 15 minutes, but we can also say 14% of the patients waited 15 minutes. So we're still giving basically the same type of information, not even just same type of information, we're really giving the same information. We're giving a count for the patients that waited 11 to 15 minutes, but now we're doing it as a percent rather than as a solid number, an absolute number. And this is often useful because, here, so for instance, here it's 50 minutes, but let's say we are 50 patients. Let's say this urgent med tested this again, but they did this for 2,000 patients, right? The numbers that they're going to get here are going to be a lot bigger, but the percentages might be similar. So what I'm saying is, if we did this for 2,000 patients, you're going to have a lot more than 7 patients that wait 11 to 15 minutes. But the key thing that we'd wonder, that we'd want to study, that we want to figure out, maybe as the manager of this urgent med, is the same percentage of patients waiting 11 to 15 minutes. So we just figured out of these 50, 14% waited 11 to 50. If I did this on 2,000 people, 2,000 patients that come in, am I getting the same results? Is 14% of the students, I keep saying students, as 14% of the patients, are they waiting 11 to 15 minutes? Because then we can make a comparison. We can make a comparison between these scenarios that are different, or maybe make a comparison between one urgent med and another urgent med, right? So maybe there's one urgent med out in the country, maybe, what do you call it? I can't remember words right now. Maybe out in Florence, that obviously is not going to see as many people as maybe an urgent med up on Broadway in San Antonio. But we still want to be able to compare the two. So how well do they take care of these patients? What's the wait time? So you don't want to compare them with absolute numbers, with a frequency that's just the absolute number, because obviously the Florence sees a lot less people. That number is never going to match Broadway in San Antonio, but the percentages could be exactly the same, which means, again, for not only the manager of urgent med, but maybe the company that runs urgent med, seeing the percentages match means that both of these urgent meds are being run just as well, or at least the same, right? Whereas maybe there is another urgent med where suddenly there's a lot less people that are getting the 11 to 15 minute wait time. So then there's something wrong there, and you need to talk to the manager there and figure out how to get that wait time down, right? So it is often, not just often, it's really often useful to compare percentages for your frequency rather than absolute numbers, because situations we're looking at are not always there. Maybe they're similar, but they're not equal, right? So they're small urgent med versus a big one. But we still can compare, in this case, wait times. and see how well these are being run if we use percentages. So anyways, so that's kind of an idea of why you might use relative frequency percentages rather than the other. But 14%, so 14% of our patients waited 11 to 15 minutes, and then you can keep doing the same thing and figure out the percentages. So literally a relative frequency table is you just replace the frequency with the relative frequency, with the percentage. For the sake of kind of doing this on the board, and since they already have this here, I'm just gonna add the relative frequency column there. But usually they would just have it replaced, but either way. So let me have you guys actually finish the relative frequencies out. So go ahead and figure out the relative frequency for 16 through 20, 21 through 25, all the way down. So go ahead, I'll pause on my side, you pause on your side. All right, let's see what you got. So 9 out of 50, so now I'm not gonna write all the calculations, but 9 out of 50, that's 18%. So the second one is gonna be 18%. And 15 out of 50 is 30%, so the third, so 30% of the patients waited 21 to 25 minutes. 9 out of 50 is again 18%. 5 out of 50 is 10%. Now I can. 18%, 10%, 6%, 4%. So that should have been your relative frequencies. Now, once you have these relative frequencies, they can ask you, just like they did in this problem, they can ask you to make a histogram, a frequency polygon, and then an ogive out of that. I think that, again, for the sake of time, because it's getting a little late on my side, let's make the histogram, and then like we saw in the last example, once you have the histogram, you basically have the frequency polygon. You just have to mark the midpoints, you know, mark the points, the values on the midpoint. And then for the ogive, you would then make your cumulative relative frequency or your cumulative frequency using these percentages, and then you would graph that out as a line graph. So it's the same process from there. But let's try to get a histogram of this going now. So I'd like you guys to make a histogram of this relative frequency. And this time you're the one setting up everything. So here are your classes. So this will help you set up the horizontal line or horizontal axis. Here are your percentages. That's what you're going to be using to set up your vertical. So you do the thing all the way through. So pause on your side, I'll pause on my side. See if you can come up with a histogram. All right, so let's see what we get as a histogram here. So let's see. So first I'm looking at this for, let's see. For the horizontal axis, for basically the classes. So it looks like we have 11, 15, 16, and 20. It looks like one of the reasons I picked this honestly is looks like I can count by fives and I can kind of catch everything. So it looks like I can start at 10 and then just count by fives and kind of get everything I need. So we need out to 45. So 15, 20, 25, 30, 35, 40. Okay, awesome, good enough. Now the vertical axis. So the highest I have here is a 30%. I kind of have everything's at least an even number, which is really nice. Also why I chose this problem. You divide by 50, at least, well, yeah, you divide by 50, you always get an even number. So they are sort of, they're not, you know, they're off of, you know, your other divisions or your normal divisions, you know, by 4, by 6. So if I counted this by 2, if I started at 0 and went to 30, I would need 15 lines to get there, which is gonna be a little overcrowded. So I think what I would do here, it would be pushing it, but I would probably, let's see. Counting by 4, I think, is the next natural thought, but the problem is, so 6 is, so that catches there. 6 is halfway. That's fine. I guess 18 is halfway between 16 and 20. 10 is halfway. I guess we can catch all these by counting by 4. So we can count by 4 up to essentially 32. And that would get us there. Another way to do this is you could count by 3s up to 30, so you'll have 10 lines, which I feel like is stretching it. That's kind of the most that you want to see. That would get us 18 exactly, it'd get us 30 exactly, but 10 would be off. It would get us 6 exactly. So you kind of have some choices here. You could count by 3s and get about half of these numbers right on. The other ones, though, would be off, like a 4. You'd have to, visually, you'd have to know that you're kind of 1 above the 3, right? Or like the 14, right? Would be kind of 2 above 12. So you visually, the person reading this might have to make some guesses with the 14 and the 4. Or you could count by 4s, and even though you're not going to hit a lot of these exactly, they're all at least halfway between the measurements. And so I think it's a good toss up. Like I said, again, that there's some subjective aesthetics things here. There isn't necessarily a right answer. So you could count by 3s or 4s, and I think you can make good argument either way for the reader, which is better. I think I'm gonna go ahead though and just count. I'm gonna do by 4s. We're gonna start at 0, and then that's 4, and then that's 8, then that's 12, and then that's 16, 20, 24, 28, and 32. That'll cover all my percentages. So these are all percentages. So then 11 to 15 was 14%. So from 11 to 15, I guess we'll go ahead and have these meet. I'll be honest on this one. So like I was saying earlier, this book does the version where it kind of has the I call it the bars meet each other. When I do that, I honestly just draw it on the line. I don't actually try to draw the 0.5, and I'm fine with you guys doing that. So if I'm gonna do kind of what the book wants, I'm gonna break the rules a little bit on that. They're already breaking the rules anyways, so I'll break the rules with them. So let's see, 11 to 15. I'm basically gonna count this as 11 to 15. So 11 to 15 is 14%. So let's draw that at 14%. And then 16 through 20 is 18%. So then let's draw that at 18. So that'll just be my 16 through 20. And then 21 through 25 is going to be 30%. So that's really obviously our highest one there. And then 26 through 30 is back down to 18%. And then 31 through 35 is back down at 10% then. Like that. 36 through 40 is at 6%. Halfway between 4 and 8. Then 41 through 45 is at 4%, so right along this line there. There you go. That would be the histogram. So this is a histogram of the relative frequency table. Again, if we had a little more time, what you'd find. So one of the cool things to do with a problem like this is draw the histogram for the frequency table. So the absolute values, and then draw the frequency grant or the histogram for the relative frequency. And what you'll see is that, and it kind of makes sense that, but they look the same. So your scaling on this axis is gonna be different because it's now you're trying to get up to 15. Maybe you count by twos or something like that. But but the overall shape, the distribution is gonna look exactly the same. You literally are gonna get essentially like just a sized up or sized down photocopy of this, essentially. So whether you use the absolute numbers or this, the overall distribution, the shape of that data is the same. Like I was saying, in a lot of circumstances, when you want to make comparisons between one thing and another, the percentages are, that's literally what percentages are for, to compare one amount to another. So you use relative frequency, especially when you want to do comparisons. You use the actual frequencies when you just want to know something about that one particular experiment or that one thing you're doing. So you just want to focus on the one. But good. And again, you could then go do the frequency polygon and you could do the ogive. So you could go through all that. Really quick, I showed you guys those distributions, those shapes of the data. What would you say this one is? So out of those that we listed, what would you say this one is? And I'll give you a second to look back at that and see if you can see what you say. So if you look at this, so what did you guys think? And I think this is an interesting one to ask a question about. So you might be saying what it would be like skewed right. And I would say that that's correct, or that you could call this skewed right because the middle is not exactly in the middle of the whole scale, right? The middle kind of sits a little to the left. So we kind of have a hill that's been pushed to the left. We still got a hill though, so this is definitely skewed left. It's not one of the J's. Um, but it's maybe, so it's pushed to the left, so it's skewed right. But you could also make an argument, so if some of you said that this is what do you call it, a bell shaped, you could actually make an argument that it's a bell shaped. Because, I mean, again, this middle it definitely looks visually like it's to the left. But the point of that bell shaped is that, it's not always going to be perfect. The data is not always going to look perfectly like center, tailored on both sides, exactly symmetric. Again, because it's real world data, you're allowed to have some discrepancies, right? So you could make an argument that this is still sort of close to, that this is still kind of bell shaped. It's high in the middle, it goes down to the left and the right. It's not exactly symmetric, but it's close. So again, statistically, you can make an argument either way. I still think it's probably closer to a right skewed. So this is closer to a right skewed because it's definitely higher on the left than it is on the right. And that's really kind of the uh, the telltale mark. That you kind of have the middle that's pushed, that's not exactly in the middle, it's pushed to the left. And the right side definitely goes down a lot farther than the left side. So you get sort of that hill that then curves down. So again, some of the subjectiveness of statistics versus those exact answers you always got in algebra. Okay. Well, that's all this homework, not just this homework, but that's all this sort of first bit of work. So basically, if you have data between these first two lectures, you should now be able to make a frequency table or a relative frequency table out of it, and even extend that into a cumulative frequency table. And then from each of those, you should be able to make a histogram, a frequency polygon, and then from the cumulative frequency, you can make the ogive. And that is awesome. All right, I will see you guys for next week's lectures 2, 3, and 2, 4. See you then.